Hello everyone, welcome back to the lecture. So today we're going to be looking into chapter 2, section 2.5 to 2.6. So from this section, the student will be able to represent a 3D vector in a Cartesian coordinate system. They also will be able to find the magnitude and coordinate angles of a 3D vector, and finally you're going to be able to add these vectors in a 3D space. So what are the applications of this section? So let's assume we have a power pole. So this power pole is staying upright. How is possible to withstand all the high winds? It's because of these guys A and B holding them upright. So we need to know what are the forces of these wires that is holding up our power pole. So maybe the FA and FE. So if we know the forces, then we can determine the power pole size and also how about the wind and everything. So we would be able to present these forces in our 3D vector form so that we can find the resultant force to keep our pole upright. Similar thing, we can also look into a radio tower where you are going to be holding it up with 600 Newton, 800 Newton and 400 Newton. So we should be able to know what will be the resultant of these three forces so that the radio station is upright or it can withstand all those forces. So this type of problem we will be dealing in this chapter. Okay, so let's look into what is Cartesian unit vectors. So let's assume you have a vector A. So we are having a vector A. So I'll be using a bold letter for representing my vector, or you can also represent it with an arrow. Anything is fine. Then I'm going to have a vector of magnitude A. So that's the magnitude, so that's not bold, so that's a normal letter. So what will be my unit vector? So my unit vector, it can be represented as my vector divided by its magnitude. So that's my vector A divided by its magnitude. So it's going to be my unit vector. So this unit vector, what is the magnitude? It's always going to be 1 because it's the vector divided by its magnitude. So its unit is always unit 1. That's why we call it as a unit vector. And it doesn't have any dimension because we are dividing a vector by a vector, so no dimension. So it has no units. And it always points in the same direction as our original vector because that's the vector. For example, my vector is vertically A. So I'm going to say that my unit vector, that's let's say UA, that is also going to be the direction of A. So this unit vector is a Cartesian axis system. We get it in I, J, and K. And they are unit vectors along positive X and Y, Z, and direction. For example, let me assume we have X, Y, and Z. So the unit vectors in those respective axes is going to be I, and it's going to be J and K. So this is like a pair. So you should always remember that I is going to be the unit vector in the axis X, and Y is going to be unit vector in axis Y, and K is going to be the unit vector in axis Z. So that's what it represented. And we are going to be using our right hand rule so that always our thumb, it points out our Z direction. And when you come in the right hand clockwise direction, you're going to be coming from X to Y. So that's how we get our directions. Okay, so let's look into the next slide. So in this next slide, we'll consider a box with forces AX, AY, and also AZ. So these forces are acting in our X, Y, and Z direction respectively. So how can we represent our vector A? That's our vector A. So if you look carefully, the vector A, the forces resolve. For example, we looked into the 2D space. So if we resolve the vector in X, Y, and Z. So those are the components of our vector A. So we can give it in vector A in a 3D space, or else we can give it in all X and Y and Z in terms of AX, AY, and AK. So how can we represent that in the Cartesian vector format? So that we get our AX, we say, okay, the magnitude of in X direction is AX, and what's its direction? It's unit vector because that's in the X. So we gave it in a unit vector in X direction. Then in y, our magnitude we know it's ay. Then we gave it in a unit vector k, j, which is corresponding to y. Then we know the magnitude in z direction is az, and then we give it in a unit vector k, which is in the z direction. So this is how we represent our 3D vector. So any vector in a 3D direction, you give it in the x, y, z coordinate, z directions by giving the unit vectors and the magnitude of those vectors. So the projection of an A in the xy plane is A bar. So what is projection of A? So that's this A. So we get the A in our xy plane. So that's, let me say this is my xy plane. So how we get that? So that's my xy plane. So this A force we can give it in AX and we have AY, right? So we can say the resultant of these one two is going to be my A prime. So that's why the projection of this A in our xy, we are giving it in A prime. So this A prime is going to be our resultant of AX and AY. So how do we find the magnitude? From previous lecture, we know we can find the magnitude by getting the square of this one. So we get the magnitude of A prime. Now we know that vector A, and now we have vector A prime. So let me get that clear here. So now, because of our three forces, we have resolved the two forces. So now our vector A, we have it as, so vector A, we said we have A as AX, and we have the AY component, and then we went for the AC component, right? So we get the resultant of AX and AY, so that makes us to clear our AX and AY. So we have it in terms of A bar. So now we have A bar and then we have AC. So how do we get the resultant of that? Again, we can use them as two forces, and we can get the resultant simply by getting the square root of those two forces. So that is A prime square plus AC square. So what is our A prime square? That is AX square plus AY square. So this gives us what? So any 3D force, any force acting in a 3D direction, 3D, for example A or B, you can get the magnitude by getting the square root of all the squares of the components in X, Y, and Z direction. So this is similar to the one we had in 2D, where you get only the two forces. But here we have third direction, also it's simply the addition of that. Okay. So direction of a Cartesian vector. So the direction or the orientation of the vector, how do we define it? By angles alpha, beta, gamma. So how are we going to see what is alpha, beta, gamma? Let's see. So this is my vector A that I was looking at. So we have this component A, Y, A, J, B. So that's my unit vector in direction of A. So what is my alpha, beta, and gamma? So alpha is going to be the angle between my vector and the x-axis in the anti-clockwise direction. So it's not the clockwise, it's just the anti-clockwise. So you should be careful with that. So you have the vector, and then you have the x, and then that's the angle alpha. And beta is going to be with y-axis. So alpha is for x, beta is for y, and gamma is for z. So beta is also going to be the angle with my y-axis, and my gamma is going to be with my z-axis. So the angles are measured between the vector and the positive x, y, and z-axis respectively. Their range is going to be always value 0 to 100. So this trigonometry direction cosines are found using cos alpha is our ax by a, cos beta, and cos gamma. So these angles are not independent. They must satisfy the following equation. That means we use cos rule. So that should be all the addition of the cos of all these three angles should be equals to 1. So they are dependent upon one another, right? So they are not independent. So let's look into the direction again. So this result can be derived from the definition of a coordinate direction angles and the unit vector. So recall the formula that we use for unit vector for any position vector. So we said that our unit vector is our vector divided by the magnitude. So our vector, we can write it in all the three directions, then we can divide by our magnitude. Then we know the unit vector, we can also give it in cos alpha I. Why we are giving in cos alpha I? So for that, we need to go to our previous slide. So here, this is our unit vector, right? So it's ax over a. So we have an I over here, and then we have j and k. So here we are taking the cos alpha and putting it there. So we can give it another way. So our ax over a, we know what is that? That's our cos alpha from the previous slide. And ay over b, that's our cos beta. And this one is our cos gamma. So we can write it in that way too. Okay, so that's simple. Now let's look into the next slide. So the addition of Cartesian vectors. So once we know the individual vectors, we can write them in the Cartesian format. And then it is easy for us to add or subtract. It's similar to the 2D forces. So you know the forces in x and y and z, we're just going to be added. This process is essentially same as our 2D one. So we have a force. Let's say we have all the three components. We just add all the three components in all the three directions. For example, let's say we have a force A and B. We have a vector A and B. So all the three components is there. How do we get the resultant of that? We are going to add the x component separately, y component separately, and our z component separately. Then finally, we have our AB. The same thing you can do the subtraction. You can just subtract the similar components in the same direction. Okay, some important notes to be noted. Sometimes 3D vector information is given. You are sometimes given the magnitude and then you are given the three coordinate angles. So then you can easily get our forces in one direction. Sometimes you are given the magnitude and you are only given two of your coordinate angles. So you're not given the third one. So how do we find the third one? We can again use our law because we know those angles are dependent. So we use this law to find out our third angle. Sometimes the magnitude and the projection angle is given. So projection angle is what it makes with our plane. So rather than giving what all the forces makes with the axis, sometimes you might given some other angles, right? Some other needed trigonometry angles, so which you can use it. So you use trigonometry to solve the problems. Okay, let's look into this problem. We have two forces F and G. So F is of 100 pounds and then you have the G force. These are applied on the force F is shown and it makes an angle 60 degrees with the XY plane. So that is a projection angle. You are not given the coordinate angle because if it is coordinate, they would have given like alpha, right? So it's a projection angle. Then you are given the force G that is pointing up, which is the magnitude of 80 pounds. And but for that, you are given alpha and beta, which is our coordinate angle. So we know that two angles and we know how we get the next angle. So we look in the previous slide. So what's our plan here? So we're going to use trigonometry and our geometries to find out the F and G in Cartesian vector formats. Then we are going to add them. Okay, let's look into solving this problem. Let's look at our F force first. So we know that F is 100 pounds. And we know what angle it makes in the XY plane. So we know that, let's take our F in the so we have the F force and they say with the XY plane it makes a 60 degrees. So first what I'm going to do is, let's go back. So this is my F and I know what it makes in the XY plane. So I'm going to find the component of X in the XY plane. So that's this force over here. So since I know this one makes a 60 degrees, so that's going to be F, which is its component, so that's cos 60. So if you look that clearly, so we have F, which is 100 Newton, which makes us 60 degree within our XY plane. So I'll take this plane. So if you consider this plane as one plane, like maybe like horizontal and then you vertical. So you have 100 Newton here. So you have a 60 degree. So what will be this force? So you can use cos 60 of that triangle. So which gives me the F prime divided by 100. So therefore my F prime is going to be 100 cos 60. This one we looked previously in the 2D forces. So there I get 100 cos 60. So now I have formed this 100 Newton in my XY plane. So I don't have the 100 Newton force here. So I have in XY plane and then I can get in the Z direction, which is 100 sine 60. So I have already one force. So now I resolve this force into two directions. So I have Z and F prime 1. So are we done here? No, we only have Z. We need to get it in X and then we need to get it in Y planes. But I have in XY plane. So consider thing like as a one plane. So now imagine this F prime as an XY prime. So I'm going to draw here in Y and F. So I'm drawing this one over there. So I know that my F is acting like that, 50 pounds, right? So I had to resolve that in X and Y direction. So that's what's shown here. But I know what is that angle it makes. So it's simple. So if we know that one, so the axis near to that, we are going to get what 50 cos of that. The axis opposite to that, we are going to get sine of that. So that gives fx and fy, which gives cos and sine factors. So we have fx and fy. We already find the z, so we can write it in the Cartesian vector with the magnitude and then the I and y take direction. Now let's solve for g. For g, we know alpha and beta, so we don't know gamma. So we are going to use our rule to find out our gamma. And from solving that, we find gamma as 30.222. So now we have cos alpha from the unit vectors. We can use this rule, we know this. So we can find out the force. So we know cos alpha I, cos that is our unit vector. And we know what is g. G is going to be the magnitude of g times our unit vector. So what is our magnitude? That is 80 times our unit vector. We write the unit vector over there. So that's simple as that. Now we have F and G, so we can get the resultant by adding the two forces. So fine. Okay, let's look into this problem. So we have two forces F1 and F2 which act on the screw I. So if the resultant force Fr has a magnitude of 150 pounds and the coordinate direction angle is also given, so you're asked to determine the angle gamma and the magnitude of F2. So let's look into this problem. So we have F1 and F2. So in this case, they are given the resultant of our two forces, that is 150, and we don't know what is the F2, but we know what is F1. And also the coordinate direction angle of Fr is given, that is alpha, and our beta and gamma is also not given. So they are asked to find out our gamma and then our F2 and also coordinate direction angle. So first they ask gamma. So gamma is how are we going to do? It's simple because we can use our rule. So we know that resultant is F1 plus F2. We know our F1 is 80J because it's a horizontal force, but F2 is unknown. But we know our Fr. How do we get our Fr? Fr is going to be how we found in the previous one. So Fr is going to be the magnitude of Fr into our unit vector. So how we can find unit vector? We can find it in terms of cos alpha I plus cos beta and then plus cos gamma. So how do we find gamma? We know that cos all this square is equals to 1. So from that we can find gamma. Then we can write it as a unit vector, and from there we can find our FR. So that's how FR is given. And from there we can find our F2. So the magnitude can be found by getting all this one. And then we can find from the magnitude, and then from the unit vector we can get our F2. So that's how you solve this problem. Then we have this problem where you have asked to find out the force in the Cartesian vector form. You can try this on your own, and let's see how the solution is going to be. Just give a try and see how it's going. So try to solve and get the forces. So you can pause the video and try it on your own. Once you are done, we can come back and check your answers. So be honest, just pause the video and try it on your own. So that will be a best practice for you. Okay, I hope that you solved the problem, or maybe at some point, at some step, maybe you're stuck at somewhere. So let's go and see that. So let's take my force F1. So where is my F1 acting? Is it acting in all the three dimensions, or is just in one plane? Yeah, so my force is only acting in the X and Z plane. So that will make our task easy, because if one force is only acting in one plane, the third direction component is going to be 0. So we know that it only has two components. So that's my X and Z. I had drawn it in a separate one, and I know my force, and I know it's 5 and horizontal 4, and then it's in Z3. So this is like a 2D force. It's easy for you. You know how to do the 2D components. So it's only X and Z components. There you get the X and Z. So I know 4 by 5 and 3 by 5 into 90. That gives me my F1. So that is simple. How about the other one? F3. F3 is only pointing in the vertical direction. That means in the Z direction. That makes us our work very easy, because it's in only one direction. So our X component is 0 and Y component is 0. So it's only our Z component. That's our 200K. So our F3 is only 200K. Perfect. Let's look into the other one. That's a little complicated one, which is our F2. So how do we solve this problem? So you can see the hint is given that it makes a 60 degree with this axis, right? That tells us this force is in this axis, in this plane, right? So like previously we looked into the problem where we have a plane. So we get it. Let's see, we take a plane, imaginary plane, which is this. So I'm going to get an imaginary plane with the Z direction and this one, some other new direction where I'm going to have my resultant force. So I say that because of this F prime and because of the vertical FC force, I get a resultant which is 150 Newton. So how do I resolve that? So this is going to be our normal 2D problem again. So I have an imaginary axis. I don't know what axis is, but I know this is the axis, but this one I don't need it. But I get the response in that. So I say because of these two forces, I get 150 Newton. And I say this makes a 60 degree over here. So from previous one, we know we can form this as the triangle, and we can get the cos, and we get F prime is going to be our 150 cos 60. How about the Z component? That's the other component. So we know for opposite of that, we get sine 60. So now this force is gone. Now I have only this and this force, because we imagine this and this forms the resultant. So we resolve these forces in the two directions. So now I don't have a resultant force. So now what do I have? So now I think, okay, now I say, I don't have this one. So now you think you have FC and this. So FC is there, done. So one direction. But this f prime is my imaginary direction. It's not a true direction, right? So I had to get it in x and y. How do I get that? It's again simple because this one is already in my this plane, right? Well, it makes 45 degree. So that's going to make my work very easy. So now it's in the 45-degree plane. So I know that cos and sine components, cos components of, because the 45 is made with the y, so the cos component is going to give me y direction force, and the sine component is going to give me the x direction force. So I have the forces. So now I have x and y forces. So then I write my force. So once I know all the three forces, what we can do, we can add all the three in the respective directions to get my result. Okay, this is the last problem. Same thing, you can take your own time, spend your time and post the video and then you can do it. So you have F1, F2 forces acting and the directions are given, the projection angles are given. So you can post the video and then you can start, and if you're stuck for something, you can come back to the video. So let's see the plan. So you're going to use the geometry and trigonometry to solve for F1 and F2 in the Cartesian vector form. Then you're going to add F1 and F2 to get your resultant. Then you're going to determine the magnitude, angles, alpha, beta, gamma of your resultant. So pause the video, then you come back and then you can do it. I hope you tried solving the problem and play the video again. Okay, let's see the problem. So we have the f prime. Let's take my f1 and I'm going to resolve that into f1c and then f prime. So where is my f force? Let's look into that. So that's my f1. So cos will give this component and sine will give that component because it's already in that way. So that's what we have here. So the cos and sine components will be that. Then we can resolve f bar again because it's make 25. So the cos component will be in y. And we can get the x component, which is going to be the other one. So now I can write f1. Then we'll take f2. So f2 is already in xy plane. So we know that the x component is going to be 0. And also we are given the coordinate direction angle. That means it's the angles with that. Sorry, it's not. Okay, it's not x is not in 0 because it makes 120. So that's the positive angle, coordinate direction angles are given. So it's simple because if we know how to get the coordinate direction angle is given, how to get the forces. So we know alpha, beta, gamma. So it's just going to be the magnitude times all our angles. So now we know F1 and F2. So we can get a resultant by adding those forces. So our resultant force magnitude, we can get it like that. Then how do we get alpha? We know that cos alpha is our resultant force over our magnitude. So our horizontal force, we know the value of that. That's this component divided by our magnitude of that. Okay, so that's all with the 2.5 to 2.6 section.